healthy kitty that ever kittied in the history of kittydom. So we have lab today. What time is it? 1:26. How is everyone else? How is everyone else doing? I just got coffee on this. There's a little coffee splotch. I was like, woohoo, I managed to take a perfect piece of paper. That was a lie. Good? That's good. Good, says Ty. All caps are great because like they add a connotation of like, I'm a little crazy right now. They probably don't deserve that. So when you see an email that's in all caps, and I have a couple of colleagues in science. That's excellent, Ty. I'm glad you made it. You've been reading The Handmaid's Tale. That book is amazing. I love that book. That is like one of the great pieces of feminist literature of all time. It is. How are you enjoying it, Victoria? Boom, 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 boom. 4 stars. If you're ever like, oh, that made you buy all her books. Yeah, I never saw the show. I never watched the show. But yeah, I definitely read The Handmaid's Tale a couple of times, and it's intense. Yeah, it's just basically like a feminist nightmare of like a patriarchy, and really thinking about what kind of decisions you have to make if you're living in like a country where you're owned, you know? And your point is not to be a person, it's to be reproduction, you know? It's, and all of the things have happened in real life. She made none of it up. Well, the color choice is a little unusual, but yeah, a lot of countries in this world are, that's its own class. Go take history and sociology, because, you know, I am very glad. I lived in Europe. Denmark's got even, in Europe, not the town, I mean, the country, the Scandinavian country, they've got even a better handle of feminism than we do. They're much more relaxed about it, and they started earlier. So I really like their attitude. But yeah, I'm glad that I live in one of the countries where I'm not owned. I can be a science teacher instead of being property. So good conversation, a little off topic. It's now 1:30. So I am going to get started on the teaching of the thingy. So there's a section, so this lab is actually 2 parts, and I've started naming the labs to make it a little bit easier to find, particularly for quizzes, and eventually the final, you'll have to go back over some of the work that you've done. That being said, the Kepler's law part is something that we've already gone through in depth, and you have all the tools I feel that you need in order to complete that section of the lab. However, we never touched on celestial navigation, and that was the section of the lab where I was literally saying to myself, like, Pearson says this should be like 20 minutes, but I don't think this is in actuality 20 minutes. Like, I don't think that Pearson is calculating understand it time. Because it's definitely, I mean, you can just guess it till you get the right answer, but there's going to be a problem on an upcoming quiz where you will have to use celestial navigation. So I recommend you don't do that. And if you get confused, ask questions, because the lab's only 10 points, but the quizzes are all 40. So So yes, don't be afraid to ask questions. So let's talk a little bit about celestial navigation, or at least the concepts that you'll need for celestial navigation. Let's switch over the camera. I really need a haircut. My hair is like totally out of control. Anyways, shouldn't be saying that, but I just, when you're staring at yourself, and I wear less makeup than I used to, but when you're staring at yourself all the time, there we go. Okay, so this is the diagram with the coffee stain. So annoying. That looks a little off color. Let me unplug, plug it back in. Usually, it's still a little off color. Can you read the words here? Can you read these words? Not really. One of my classes need me to have my camera, and I'm just like, wow, yeah. And I totally understand and support professors who do that, because like that's actually the amazing things your professors get into really heated poop about. That was two groups of people who are like, you're the one that doesn't care about the students learning, about the argument about whether or not to make your cameras turn on or whatnot. And I'm like, eventually I was just like, we're all meaning well. I'm not going to, but you do what you do. So yeah, I need a haircut. I got a split end problem. Okay, can you read it now that we're zoomed in? Awesome, thank you, Rodney. Japanese is awesome. I want to take Japanese. Anyways, but I want to learn everything. So this lab, so the second half of this lab is all on celestial navigation and understanding celestial navigation and how it works. There's two basic parts of celestial navigation that you need to understand. That one way is to find, you find your latitude. By using the celestial equator, north celestial pole, and star declination. Okay. Hang on half a second. Hang on half a second. So this is going to be a discussion of angles in here as we're working through this. So the star, you can find your longitude by using a clock. It has to be a very accurate clock, and the position of celestial objects. Let me zoom that out because you don't need that big. So what are we dealing with here? What we're talking about so you know, before you ever came into this class, that like the Vikings and the Pacific Island peoples and a variety of peoples use the stars in order to navigate. And that includes European and other explorers, you know, from China in particular, also from Japan, that also use the stars as navigation. So this particular lab is going to teach you the really cool skill of how to do that. If you have a star chart and a sky and a way of measuring angles, then you will automatically be able to find your latitude relative to your latitude from objects that you find in the sky. So I am grabbing, you might not be able to hear me, I am grabbing a protractor because my brain just said, why don't you have your protractor out? Because you're going to need that. And a protractor is for measuring angle. Now, once again, you are going to be doing this in the lab, so you will not need a protractor, but I need a protractor in order to get the angles even remotely correct. So, because I lack art skills, I think we have established that. So, moving forward. Okay, so what we have here is a diagram to help us understand some major features of the celestial sphere that will help us identify or help us calculate where we are in latitude and in longitude. So, first part here is the celestial pole. So the celestial pole, basically, if you take a dot at the North Pole and you point it out towards the sky, the North Celestial Pole is that dot out in the distance against the night sky that the North Pole is essentially pointing at. And in the northern hemisphere, what is that object? North Star, excellent. Now the South Pole does not have a single object. That's Polaris. Excellent, Patrick, even better. So the South Pole does not have a single object. It actually has a feature called the Southern Cross, which is 4 stars. And they don't even sit exactly over the South Pole. They just basically like spin around the South Pole over the course of the night. But where the end of the Southern Cross points is pointing towards a center that includes the South Pole. We then also have the celestial equator. The celestial equator, same idea as the celestial North Pole and the celestial South Pole. It's just the equator imagined up against space as a line in space. Okay, like a line at the celestial equator. Now, why do I care about celestial equators or any of that kind of stuff? Well, first of all, let's make sure that we understand latitude and longitude. So latitude is the equator or the meridian latitude or longitude? So is the equator an example of longitude or latitude? I think that I phrased that terribly crappy. It's a line of latitude. Okay, so the prime meridian is a line of longitude. That's a line that runs vertically. A line of latitude equator is an example of a line of latitude. What degree is the equator? Zero. Excellent, Rodney. So the equator is 0 degrees. So we've got 0 degrees. And on Earth as well, that equator is 0 degrees. Okay. What about the North and the South Pole? What degree is that? 90. Excellent, Ty. So this is 90 degrees and this is 90 degrees. Okay. And notice if we had an imaginary dot in the center of the earth and an imaginary dot here, that's 90 degrees from the equator to the pole is 90 degrees. Okay. Now, what was the ecliptic? Does anybody remember the term ecliptic? Because it's going to become a little bit important. The path of the orbit. Excellent, Rodney. So it's that imaginary, the ecliptic is basically that imaginary surface or circle that the Earth is basically sitting in that represents the plane of the orbit of Earth around the sun. Okay. So just seeing if you're picking up everything I'm laying down, what's this angle between the equator and the ecliptic equal to? This is kind of a geometry problem. What makes you say 45? Good guess, but that's just a guess. Think about important angles that we've talked about so far, particularly when we were talking about Eratosthenes. It's not, though. It's not half the equator and the North Pole. What's this angle in here? Oh, no, it's not. Right. I like that. Oh, wait. No, it's not. Thank you for talking it out, too, because, like, that's how learning happens. So what's this angle in here? The angle between the line which is perpendicular to the orbit and the line that represents the line through the poles. What's this angle? What is that angle? Go back in your notes. Don't be afraid to look at your previous notes. I feel like I'm either right or nowhere near correct. 35. It is 23.5 degrees. Excellent, Patrick. How do you know? Because we talked about that angle a lot, Dr. Eby, and I figured that at some point it would rear its ugly head again, which is fair enough if you're trying to guess in a multiple choice test. That kind of reasoning is excellent reasoning. I remember you talking about it, right? Why? Why do we talk about 23.5 degrees? There are two reasons. It's the tropics. Excellent, Brianna. And it's the tilt of Earth's axis. Excellent, Patrick. Both those things are absolutely true. Brianna is right and Patrick is right. So those are that is the latitudes of the tropics, and that is the tilt of Earth's axis. We're going to go very geometry up in here. Okay. So this angle right here is 23.5 degrees. Okay, we're gonna imagine this right here. Let's have the sun over here and make sure that we label this as the position at the December solstice. So we're gonna say this is the position at December solstice. Okay. Now that's not going to make any difference for our navigation, actually, but that is going to make a huge amount of difference. Well, it will make some difference for our navigation when we're talking about the sun. But so our December solstice, we have this tilted away from the perpendicular to orbit. This is the axial tilt or the obliquity. Then over here, how many degrees is the ecliptic from this perpendicular, this line that's labeled perpendicular to orbit? How many, what's the degree angle in here? Between basically this angle to this angle. This plane right here and this line right here and this line right here. What is this angle? Good thought, Rodney. We're talking about, here, let me highlight this angle. We're talking about this angle right here. It says it's perpendicular to orbit, and then this is the ecliptic. So what's the angle there? 90, excellent. Now, what's the angle between the celestial equator and the poles? The line between the poles. Or the axis of rotation of Earth. What's the angle between the axis of rotation of Earth and the equator? Also 90, excellent. So Brianna's got it. So this line and this line are 90 degrees from this. And this line and this line are 90 degrees from each other. So what's the angle in here between the celestial equator and the ecliptic? $23.5 degrees. Excellent, Rodney. Excellent. So this is also 23.5 degrees. Excellent. Now, why do we care about legit any of this? Because we use the equator, to the celestial equator and the celestial North Pole in order to find, and the star's declination in order to figure out what latitude we're at. So now this is an imaginary example. This is not precise because I can't draw a star like way off into the distance. But let's suppose, so let's suppose there is a star directly on the celestial equator, okay? We can think of that as the star's almost like latitude. If you cannot see, be like Dr. E, I cannot see. I know I'm really zoomed in here, but it is only because like that. So we've got a star on the celestial equator. So we would say that this star's declination, which is its difference from the celestial equator to basically its distance from the celestial equator in angle. So for example, up to 90 degrees. So basically like if you imagine it as a big sphere, a celestial sphere, it would be following up like lines of latitude. So on the celestial equator, that would say 0 degrees declination. I almost wish I let the video teach this to you instead of me, because I feel like with moving images, it becomes a little bit easier. But I just want to introduce you to some of these ideas. Now, let's suppose that we are living at, no, technically we're over here, but I'm going to put us over here. We're living at approximately 44 degrees north. If I am standing at the celestial, if I am standing at the real equator, the star on the equator will be directly overhead. Okay. However, when I'm over here at 44 degrees north, which is basically Watertown, now when I look up at the sky, that star is not directly overhead. Okay. Okay. So like if I'm standing here and I look up, I see the star straight overhead, it will pass right over my head. If I'm standing here, it's much lower on the horizon. Okay, it's much, much lower down than it would be if it were here. Okay. So basically, the declination, okay, so the distance, like that star looks like it is from the celestial equator, will be able to be used to calculate what my latitude is, because it's from that calculation, from that angle. And it's hard to understand because this is a static piece of paper. The star should be basically infinitely out, and then we would have actually the actual correct measurement here. But if I look out, infinitely out towards where this is pointing, out into the distance, okay, I get an angle with my night sky that's different than this person over here. The difference between these two tells me my location running north to south. Now it's actually much simpler to find your position in time. And it's a little bit like, have any of you driven cross country? Any of you? Like driven outside the state, like Ohio, all those places? Unfortunately, not cross country. No, no, no. Just down country, driven to Florida. I'm from the Midwest, and we're really interested in moving east or west, because other than Chicago's like a little fart of something in the middle of a vast wilderness of corn. So, so when you do drive somewhere across country, what's going to happen to the clock in your car? Is it always going to stay accurate? Like not your cell phone clock. I mean the clock in your car. Oops. I'm like, why is this a weird angle? Why am I not? Because it's this one. There we go. So what will happen? No, it will be the time of wherever you were, right? That is basically the idea of using a clock to find longitude. So longitude, if you imagine the Earth, this is easier visualizing, and it's all easier visualizing the Earth. If you visualize these lines of latitude, they're basically times, okay? Because if you're on, for example, right over here on this side of the Earth, then you are 12 hours away from the person on the direct opposite side. So does anyone know how many degrees are in basically this circle? And that's a big hint because it is a circle. Altogether, how many degrees? How many degrees are in a circle? 360. Excellent. So basically, you can do the calculation that if it's 360 degrees and there's 24 hours, then 360 divided by 24 is, I think, 15. Yeah, 15. So every 15 degrees, you change 1 hour. Okay. So let's suppose that you were in New York, New York, and 361. And you got in a boat and you started going out to sea, and it has an accurate like watch, like an old school analog clock that does not actually change. It's not like your cell phone that corrects it. No, you're in an old school boat with an old school clock. Now, if you look up at the sky when your clock says noon and you're out in the middle of the North Atlantic Ocean, let's see, New York is at 75 degrees. So let's go ahead and go to 45 degrees, which is 30 degrees different, okay? Because every 15 degrees is, equivalent to an hour, then this, like at noon on your watch, the clock, the sun in the sky is going to be 2 hours from that, where basically where you should be, where you came from. Okay, so if it's noon in New York, right? If it's noon in New York, this is terrible. Let's try it over like this. If you're noon in New York and your clock says noon, but you're out here at 45 degrees, okay? Earth turns counterclockwise, right? So, so when your clock is going to be 2 hours, basically 2 hours off of where the sun, it won't be, the sun will not be directly above your head or as at its zenith, highest place it could be. It will be 2 hours off from that position, which is, once again, I almost wish that I trusted the video to teach you, because it's moving and it's got like really good animations. And I do not. I have a crappy globe. It would be easier if you could hold the globe. All of this would be easier. So, so does anyone have any questions before they get started on this lab? It's pretty straightforward once you get used to the ideas of angles. But what I don't want you to do is to get like super stuck. And the Kepler's law stuff I'm really not worried about, because we covered that. You got quizzed on some of it. Bob's your uncle. But this celestial navigation stuff can be challenging, and I do plan to quiz you on it. So definitely, please feel free to ask questions, and that will also help me learn, because like I said, this is my first time teaching astronomy as its own standalone class at this institution. So there may be aspects to my explanation that I need to improve, and I will understand that better. You're helping me learn how to make this course better by asking me questions. So please, lots of questions. Does anyone have questions now? Okay, hearing none, I'm going to stop the recording.